Quantum mechanics. Is it a science or something else? To tackle this, we'll turn to the insights of Karl Popper, one of the most influential philosophers of science in the 20th century. Popper's critique of quantum mechanics might surprise you, so stick around as we dive into his ideas, the issues he raised, and his proposed solutions. Let's jump right in. Now, you might be wondering that, how could a philosopher, someone who isn't directly involved in the day-to-day workings of scientific research, have such strong opinions on quantum mechanics? Well, Karl Popper wasn't just any philosopher. He was a trailblazer in the philosophy of science, someone whose ideas continue to influence how we approach scientific inquiry today. Popper wasn't satisfied with just observing science. He wanted to define what truly made science scientific. Popper introduced the concept of falsifiability as a key part of what makes a theory scientific. He argued that a scientific theory must be testable and able to be proven wrong. This idea became central to his philosophy of science. According to Popper, science moves forward by disproving theories. But quantum mechanics posed a challenge to his idea. Its reliance on probabilities and uncertainty made it hard and sometimes impossible to test or prove wrong, which Popper believed made it less of a true science. Before we dive into Popper's critique, let's take a moment to understand his background. Born in Austria in 1902, Popper grew up during a time of major scientific and cultural changes. He was inspired by the scientific breakthroughs of his era, especially Einstein's theory of relativity. Popper admired how Einstein's theories could be tested and potentially proven wrong. This idea of testability greatly influenced his philosophy, making falsifiability the key to what he considered good science. Now, let's turn our attention to quantum mechanics. If you've ever heard of quantum mechanics, you probably know it's often described as weird or mind-bending, and for good reason. Unlike classical physics, which follows predictable and straightforward rules, quantum mechanics works in the world of probabilities. It's a field where tiny particles can exist in multiple states at the same time, where just observing something can change what happens, and where uncertainty is built into how things work. It's fascinating, but also really different from the science that most of us are used to. Popper wasn't a fan of this probabilistic and uncertain nature. To him, a scientific theory needed to be grounded in objective tests, not subjective observations. He specifically took issue with the Copenhagen interpretation of quantum mechanics, a widely accepted framework developed by physicists like Niels Bohr and Werner Heisenberg. The Copenhagen interpretation posits that quantum phenomena only exist in a definite state when they are observed. Until that point, they exist in a superposition of all possible states. For Popper, this reliance on observation was a red flag. He felt it introduced subjectivity into a field that should strive for objectivity. After all, if a theory's validity depends on an observer, how can it be truly tested? This, Popper argued, made quantum mechanics unscientific in its current form. It lacked the ability to be falsified in a meaningful way, which in his view was the hallmark of science. But Popper didn't stop at criticism. He offered solutions. Instead of accepting the Copenhagen interpretation, he proposed an alternative approach. Popper believed that quantum mechanics needed to evolve into a framework that was both testable and falsifiable. He argued for interpretations and modifications that could withstand rigorous testing and potentially be proven wrong. In other words, Popper wanted quantum mechanics to be treated like any other scientific theory that is open to scrutiny, criticism, and revision. Let's pause for a moment and consider why Popper's critique was so significant. At the time, quantum mechanics was revolutionizing physics. It challenged existing paradigms and offered insights into the fundamental workings of the universe. But it also left many scientists puzzled. The rules that governed the quantum world seemed to defy the logic of classical physics. Popper saw this uncertainty as a crisis. He believed that if quantum mechanics remained in its probabilistic and observational state, it risked being relegated to the realm of pseudoscience, a term he used to describe theories that couldn't be tested or falsified. One of the key issues Popper identified was the role of probability in quantum mechanics. Classical physics, with its deterministic laws, could make precise predictions about the behavior of objects. Quantum mechanics, on the other hand, dealt in probabilities. For example, it could tell you the likelihood of finding a particle in a certain state, but couldn't provide a definitive answer. Popper argued that this probabilistic nature made quantum mechanics incomplete. He believed that for the theory to be truly scientific, it needed to account for probabilities in a way that was testable and falsifiable. So, what was Popper's proposed solution? He suggested a reinterpretation of quantum mechanics that focused on objective tests rather than subjective observations. He was particularly interested in experiments that could challenge the core principles of the theory. For example, he advocated for experiments that could test the limits of quantum mechanics and potentially prove it wrong. By introducing these falsifiable elements, Popper believed quantum mechanics could move closer to being a true science. Popper's critique didn't just impact quantum mechanics. It had broader implications for the philosophy of science. His insistence on falsifiability pushed scientists to think more critically about their theories. It encouraged a culture of rigor, where even the most accepted ideas were open to challenge. This approach has had a lasting influence, shaping the way we think about scientific inquiry today. But Popper's ideas weren't without controversy. Many physicists disagreed with his assessment of quantum mechanics. They argued that the theory's predictive power and experimental success were evidence of its scientific validity. After all, quantum mechanics had been used to develop technologies like semiconductors, lasers, and quantum computers. For these physicists, the practical applications of the theory outweighed Popper's philosophical concerns. However, Popper wasn't trying to dismiss the achievements of quantum mechanics. He acknowledged its successes, but believed that its foundational principles needed to be re-examined. He saw quantum mechanics as a work in progress, a theory that had the potential to evolve into something even more robust and scientific. One of Popper's key contributions to this debate was his emphasis on the importance of open systems. He argued that scientific theories should never be seen as final or complete. Instead, they should be viewed as open systems, constantly subject to testing, criticism, and revision. This perspective encouraged a dynamic view of science, where progress was achieved through the relentless pursuit of the unknown. In many ways, Popper's critique serves as a reminder of the importance of questioning even the most established ideas. Science, as Popper saw it, is a continual process of inquiry, refinement, and challenge. To Popper, the strength of science lies not in its ability to provide definitive answers, but in its openness to revision and falsification. This dynamic nature of science ensures that it remains a robust and evolving endeavor, always pushing the boundaries of what we understand about the universe. Quantum mechanics, with all its mysteries and paradoxes, epitomizes the spirit of scientific exploration. While it may not fully align with Popper's strict criteria for falsifiability, its practical successes and the profound questions it raises have propelled humanity into new realms of knowledge and technological innovation. From quantum computing to entanglement-based cryptography, the applications of this theory demonstrate its immense value. Yet, the philosophical challenges Popper raised are far from resolved. They serve as an enduring call for deeper inquiry, urging both physicists and philosophers to strive for clarity in understanding the very nature of reality. Popper's legacy reminds us that science is not just about solving problems, but about framing them in ways that lead to greater understanding. As we continue to explore the quantum world, Popper's critiques and insights remain a vital part of the conversation. They inspire a spirit of critical thinking and encourage us to question the frameworks within which we work. In the end, the true power of science and of quantum mechanics lies in its ability to transform questions into new frontiers of discovery. And with that, we come full circle, acknowledging that the interplay between science and philosophy is not just essential, but inevitable as we seek to unlock the secrets of the cosmos. Thank you for joining us on this journey into the quantum realm through the lens of Karl Popper. Until next time, keep questioning, keep exploring, and stay curious.